Okay, now we'll talk about heat engines. Again, heat engines, what they do is they absorb heat from a reservoir, hot reservoir, convert some of that to work, and dump the rest out. And like I said, what we would ideally like is to convert all of the heat absorbed to work. We'd like 100% efficiency. But it turns out that heat is the worst form of energy, and this cannot be 100% of it cannot be converted to work. Whereas 100% of work can be converted to heat, 100% of mechanical energy can be converted to heat, but the reverse is not possible. So for instance, the world's most efficient heat engines, so on large scales are thermal power plants, and they're at best about 40% efficient. Okay. Your car is about 20% efficient. Okay. So your car is a heat engine, and let me show you a model of your car. You've seen this before, but we'll look at it again. Air fuel mixture, ignition, there's the heat and work being done, and then you're dumping out the heat that cannot be used. Heat, work, QC, you're dumping out the heat that cannot be used. Air fuel mixture, compression, heat released, work done, and the heat, unused heat dumped out. Okay. So in a heat engine, you absorb heat from a hot reservoir, do work, and dump out the unusable heat. Okay. All right, so that's what a heat engine does. It converts heat to work. It converts some of the heat absorbed to work. The efficiency is defined as how much work did you get out for that amount of heat absorbed. Okay, so here's a cartoon diagram of a heat engine. The heat absorbed from a reservoir, work done, and this is the exhaust heat. A Carnot engine, so here was the question, okay. Ideally, we'd like the efficiency to be 1. That is, all the heat absorbed to be converted to work. Now that's impossible, thermodynamically impossible. So Mr. Carnot, back in the 1800s, asked the question, what is the best we can do here? Okay. And here's the answer he came up with, and which I'll show you over the next few slides. But the answer Mr. Carnot came up with was the following. Okay, so Mr. Carnot came up with the following. Oops. If you have an engine operating between this cold reservoir and that hot reservoir, it doesn't matter how you build the engine, the maximum efficiency, which we'll call the Carnot efficiency, is 1 minus TC by TH. And these are temperatures in Kelvin scale. Okay. So Carnot says for a heat engine operating between these two temperatures, the maximum possible efficiency is that. Okay. And that's so for a heat engine, the efficiency is this, and what we are saying is the max efficiency just depends only on the operating temperature. Okay. And that's what Carnot came up with. So that's what we'll look at. Okay. So Carnot, a French engineer, showed that a theoretical heat engine in which all processes are reversible. So again, reversible processes are ideal processes, essentially frictionless processes, and no energy is wasted due to friction and turbulence is the most efficient engine possible. All real engines are less efficient than a Carnot engine. Okay. So again, The efficiency of a heat engine is W by QH. The work done is how much heat you absorb minus the heat dumped out to the environment. Okay, so this, if you substitute that here, what you get is 1 minus QC by QH. So for all heat engines, the efficiency is 1 minus QC by QH. Okay, and what Mr. Carnot showed is that for an ideal heat engine, QC by QH is just equal to TC by TH. Okay, and so you get this expression. So that's what Mr. Carnot proved. For an ideal engine, QC by QH is equal to TC by TH. Okay, so here's what Mr. Carnot showed. QC by QH would be TC by TH. Okay, so here's an ideal Carnot engine. What he showed, the ideal Carnot engine would consist of two isotherms. This is an isotherm, this is an isotherm, and connected by two adiabatic processes. Okay, so this is an ideal Carnot cycle on a PV diagram. Two isotherms connected by two adiabatics. Okay, so you are in an adiabatic process, you do not absorb heat. So during these processes, you do not absorb heat. So you're absorbing heat during these two isotherm processes. You absorb heat during the hot cycle, and you dump heat in the cold cycle on the cold isotherm. Okay, and so the change in entropy for an entire cycle is 0. The total change in entropy for a cycle is 0 because you come back to the original state, and this is 0. So change in entropy, which is change during the hot isotherm and plus change during the cold isotherm, it's equal to that, and that's equal to 0, and that's how we should TC. So that expression is equivalent to, so QH by TH minus QC by TC equal to 0, QH by TH equal to QC by TC, and that shows TC by TH equal to QC by QH. Okay, so that's what Mr. Carnot showed, and since the efficiency is 1 minus QC by QH for a Carnot engine, which is also the maximum efficiency, equal to 1 minus TC by TH. Okay. Only temperature dependent. All right, so for a Carnot engine, the efficiency is given by that. This is the maximum possible efficiency. So the temp, and again, these temperatures are in Kelvin scale. So if you put down the real temperatures for your car, so TC would be the temperature, outside temperature, air temperature. That's where you're exhausting the gases. And T hot would be the temperature of your engine block when the engine is running. If you put those real numbers in, you would get an efficiency of 70%. And the actual efficiency of your car is roughly about 20-25%. Okay. So a lot of room for improvement. All right, now we'll talk about the